To our third lecture of Chapter 2. We are going to wrap up our talk about the periodic table and all of the super cool information that is on there. And then we are going to talk about the mole, which is, obviously one of the big topics in chemistry. And we're going to see how to use that mole in different conversions. So, last time we talked about the periodic table, and we were talking about Mendeleev and how he arranged it in order of increasing atomic mass, but that Henry Moseley came through and actually corrected it to be in order of increasing atomic number, or the number of protons in the atom. And the periodic table is super awesome. It displays a ton of information, and as we go through the course, you're going to learn more and more about the information that it contains. Last time we talked about the fact, like I said, that it's in order of increasing atomic number now, and that the elements in a given column, right, in a given group going up and down, have the similar properties. So like all of these, the ones to the far left in group 1A, those are all alkali metals, and with the exception of hydrogen, and they will react on contact with water. The ones, on the far right are the noble gases, and they are completely unreactive. And so in a given, any given column, all of those elements will have similar properties, similar reactivities, which is really awesome. Another thing that we can see on this modern periodic table is that it is arranged by metals, nonmetals, and metalloids. So the ones that are all kind of this tan color, those are metals. And the ones that go down the zigzag line that are in purple, those are metalloids. And the ones all the way to the right that are in green with the addition of hydrogen, those are all nonmetals. And they all have different properties, right? Metals are different than metalloids, which are different than nonmetals. So we're going to go through those. So metals lie on the lower left side and the middle of the periodic table, and they have some common properties. They are really good conductors of heat and electricity. And you will know this if you, touch your seatbelt. That buckle, right, when you get in the car on a really hot day, really good conductors of metal, or of heat. And we know they're good conductors of electricity because of things like copper wire, right? That's what, electricians use in your house. They can be pounded into flat sheets, which means they are really malleable. You can think about tin roofs and things like that. They can be drawn into wires, which means they are ductile. They are often really shiny. They tend to lose electrons when they undergo chemical changes. This one will be really important as we move forward in the course. They lose electrons. They make positively charged ions, which are called cations. And then these are just some examples: chromium, copper, strontium, lead, right? Those are typical metals, and I think in general we're kind of familiar with what a metal might be. Nonmetals lie on the upper right side of the periodic table, so totally the opposite from the metals. There are 17 total nonmetals. 5 of them are solids at room temperature. So this is carbon, phosphorus, sulfur, selenium, and iodine. 1 of them is a liquid at room temperature. That is bromine, and that's this cool amber-colored liquid down here. It's really pretty. Also, I just noticed just how it's showing up on my iPad. That is not carbon. That is not carbon. This is sulfur. Sorry. Sulfur is a yellow substance, and it smells really bad like rotten eggs. So if you've ever been to Hanford and maybe drank some of the water there, you may have noticed that they have a high concentration of sulfur, which makes it smell a lot different than water you might have other places. And then 11 of these are gases at room temperature, and you can see them all listed there. If you look on a periodic table, so not on this one, but you'll often see that the elements have different colors, like, a lot of times like helium and neon and argon, krypton, they may be written in a color other than black. A lot of times, like the one in our classroom at COS, they are written in red, and that shows that they are gases at room temperature. A lot of the metals are written in black. The liquids are often in blue, which is like mercury is a liquid, right? And we have bromine, which is a liquid. Yeah, so anyways, just if you see that the letters are written in different colors, that is telling you the states of matter, which is really cool. It doesn't have it on that periodic table, but it often does. And then as a whole, back to this, nonmetals tend to be poor conductors of heat and electricity. We often think of them as insulators. So they don't conduct heat, they don't conduct electricity, they're not ductile, they're not malleable, and they tend to gain electrons when they undergo chemical changes. So essentially, this is totally the opposite of the metals. So if you remember all of the properties of the metals, you can essentially know all of the properties of the nonmetals because it's exactly the opposite. There you go. Metalloids, those ones on the diagonal, are sometimes that you'll hear them called semimetals. Essentially what it is that they have properties that are between metals and nonmetals, which makes sense because literally on the periodic table, they are between the metals and the nonmetals. Sometimes they behave like metals, sometimes they behave like nonmetals, and a lot of times you can actually control how they behave by changing the conditions. You can change the temperature, you can change the pressure, and by doing that, you can make them act more like a metal or more like a nonmetal. Super cool. Several metalloids are classified as semiconductors because they have intermediate electrical conductivity, and it's really temperature dependent. So because of this, metalloids are used really frequently in electronics. Like you've heard of Silicon Valley, right, over by the Bay Area, and that is because they use a lot of silicon in their technology, and silicon is a metalloid, right? And they use a lot of silicon in those electronics because it has these properties for this electrical conductivity. Makes it really awesome for electronics. So here's a periodic table. We have a couple different classifications. So we have main group elements, which are the elements to the far left and the far right. So if you ever hear me talk about main group elements, that's what I'm talking about. And then the transition elements are the ones in the middle, these guys. And you'll often hear them called transition metals or transition elements, but that's what those are. We have two different ways of talking about the group numbers. So the group numbers are these numbers on the top, right, like 1A and 1. So if we're talking about the A series, then we number this as 1, 2, 3, 4, 5, 6, 7, 8. And a lot of times that's how I will refer to them. I'll often drop the A and I'll call them group 1, 2, 3, 4, 5, 6, 7, 8, which isn't quite right, but it's just those are the ones that we normally talk about. If we were going to number all of them, then it goes 1 through 18 and just number straight across. So the main group elements are the A series, and the ones in the middle, those transition elements, are the B series. They don't go in order though. This is 1B, 2B, and then it starts over here. But like I said, normally when we are going to number these elements, oftentimes we're just talking about the main group elements. So we go 1, 2, 3, 4, 5, 6, 7, 8. That'll be really common when we start getting into bonding and things like that. But I'm just pointing out that there are two different numbering systems to the periodic table. So here are the names of some of the groups, and I do want you to know these. Okay, so the representative elements are often called main group elements. Those are like the same thing. Okay, so representative elements, main group elements, all kind of the same. Anything in group 1 or group 1A are called alkali metals. Group 2 or 2A is called alkaline earth. We talked about the transition elements in the middle. The ones that are group 3A through 6A don't have common names. Usually if we'll talk about those, we're going to say like carbon's group or oxygen's group or boron's group. We'll usually talk about it like that, or we'll just simply say group 6A. But this one has a name, right? The halogens and then the noble gases. So I do want you to know these four names as well as the transition metals in the middle. Really briefly, we're going to talk about the formation of ions really briefly because we are going to get more into this when we talk about bonding. I just want to talk about it in this chapter because it's introduced in this chapter. So when we form ions, the metals will lose electrons. Okay, so like sodium is going to lose electrons and chlorine will gain electrons. So metals lose electrons, nonmetals gain electrons. So when we are forming this ionic bond, sodium takes its electron and gives it to chlorine. Okay, so when we look, sodium now has lost an electron and chlorine has gained an electron. Okay, so if you're asked to write the protons, neutrons, electrons of an ion, right, like sodium Na plus or Cl minus, The plus tells you it has lost an electron. And the reason it's positive, right? Electrons are negatively charged. So if sodium loses something negatively charged, it now becomes positively charged. Okay, the protons remain the same, the neutrons remain the same, but the electrons are what changes when you have that positive charge. Okay, so now if you look, we have 11 protons and 10 electrons, so we have one more positive charge than we have negative charge, which is causing this positive here. If we have Cl minus, that tells you that that has gained an electron. The protons stay the same, the neutrons stay the same, but the electrons have changed, right? We have one more positively charged electron than we have protons. So we have, you know, the electrons, that negative charge is outnumbering the protons by 1, which is causing this negative here. Okay, so if you see a charge on the atom, that is telling you that it has changed the number of electrons. A positive means it now has less electrons, and a negative means that it now has more electrons. So we can actually predict the charges that these are going to make, and I would like you to start memorizing these charges. Hopefully you're familiar with some of these from previous courses, but anything in group 1A will make a 1 plus charge. Anything in group 2A will make a 2 plus charge. Okay. Anything in group 3A, mostly, that does ionic bonding will make a 3 plus charge. Anything in 5A will make a 3 minus charge. 6A will make a 2 minus charge. 7A will make a 1 minus charge. And the noble gases do not form ions. And we will talk about this all more, like I said, as we move forward. But so this is going to be plus 1 or 1 plus. This is plus 2. Actually, here, let's write these the other way. 1 plus, 2 plus, 3 plus, and then these guys do not do ionic bonding, so don't worry about them. And then 3 minus, 2 minus, 1 minus, and again, these guys do not do ionic bonding. Okay, so there's a pattern. 1 plus, 2 plus, 3 plus, skip, 3 minus, 2 minus, 1 minus. And that's how I would remember it. So if you're looking for ways to memorize, you know, it goes up, 1 plus, 2 plus, 3 plus, and then we'll skip the 4A, and then 3 minus, 2 minus, 1 minus. So it counts up to 4A and then counts down. And then again, skip the noble gases because they do not form ions. So these are elements with predictable charges. You have a table, you will have a sheet, essentially, in the next chapter that has ions with not predictable charges, aka these transition metals. And those ones you get to memorize. Yay, you. You won't be doing all of them, but you will be doing quite a few of them. So I would start working on these ones, the ones with predictable charges that follow this pattern, because soon you're going to have to do these transition metals that do not follow a pattern. Okay, on to the mole. Hopefully you've heard about the mole, and it is not this cute little guy down in the bottom right. We often use the actual mole, like that guy, as kind of like a chemistry mascot, right? Because we talk about the mole all the time. But the mole is a chemist dozen, and we use it to count really large numbers of objects, like atoms. And so we use this because atoms are really, really small. And you're familiar with these words that mean numbers, right? Like a dozen means 12. A baker's dozen is 13. A gross is 144, which you may not be familiar with. And all teachers are familiar with a ream, which is 500. And so again, we use this term, the mole, which is abbreviated MOL. I know that's not a great abbreviation. All you did was drop the E, but it is. And the mole is 6.02214 times 10 to the 23rd particles. And the reason that we use this really large number is, again, atoms are so small, right? So we need a really large number to make it so that we can actually count them on kind of a laboratory scale. So 1 mole is 6.022 times 10 to the 23rd. And that's usually how we'll use it. We'll use it 6.022 times 10 to the 23rd. You can use it with all of those 6.02214 if you'd like, but it's a little bit overkill. Usually 4 significant figures is going to be plenty for our calculations. And this number, we call it Avogadro's number. Fun fact, it was not actually discovered by Avogadro, but it was more named in his honor. But more on Avogadro and all of that later. So, the mole can specify Avogadro's number of anything. So, for example, if you had a mole of puppies, then you would have 6.02214 times 10 to the 23rd puppies, which would be a lot of puppies. You could also have a mole of sand, right? Use 6.022 times 10 to the 23rd sand grains. It doesn't have to be atoms or molecules. It could be anything. Like you could have a dozen people or a dozen cookies, right? The dozen means 12. Doesn't matter what the thing is. So here, 6.022 times 10 to the 23rd is a mole of whatever it is that we're talking about. And the way that it is defined, just if it comes up, the value of the mole is equal to the number of atoms in exactly 12 grams of pure carbon-12. So if there were no carbon-13, no carbon-14, we just had pure carbon-12, and we measured out 12 grams of carbon-12, then there are 6.022 times 10 to the 23rd atoms in that amount. So we said, okay, 6.022 times 10 to the 23rd atoms, that is equal to 1 mole, which is equal to 12 grams. 12 grams is the molar mass, or the mass on the, of 6.022 times 10 to the 23rd atoms of carbon. So these conversion factors here will be very useful. You can use the mass on the periodic table, that's equal to 1 mole, and 1 mole is equal to 6.022 times 10 to the 23rd atoms. Okay, but it came from carbon. A lot of things that we do are based on carbon. So here is an example of how we would use this to do calculations. So in this one, it says how many moles of silver are in, silver atoms are in 2.80 times 10 to the 22nd silver atoms. So again, we're going to use this dimensional analysis that I talked about before. So you're going to figure out what you're starting with, right, which is this. 2.80 times 10 to the 22nd silver atoms, and figure out what you're trying to convert it into. So we're trying to turn it into moles of silver. So the number that we're starting with is always going to go in the beginning of the train track. And sorry, I'm going to turn off my volume here. Is always going to go in the beginning of our train track, right there. And then we need to figure out how to cancel atoms of silver to get moles of silver. And like we just talked about on the previous slide, we know that Avogadro's number, right, 6.022 times 10 to the 23rd atoms is equal to 1 mole. Okay, so if we have atoms of silver here, our units are always going to cancel down and to the right. So if we have atoms of silver there, then down and to the right, we need to have atoms of silver. That means that this part is going to go on the bottom, and this part will go on the top. Remember, when we do dimensional analysis, we do these train tracks, when things are equal, they get stacked. So this side will go on the bottom, right, that atoms of silver, and then 1 mole will go on the top. Okay. When you are doing these train tracks, this dimensional analysis, please always include the number, which is like 2.80 times 10 to the 22nd. Also include the unit, like atoms or moles, and then include the chemical, like silver. And you need to have those 3 pieces of information, because as we move forward, it's not always going to be silver, silver, silver. Partway through, you're going to change from, silver into silver chloride or something like that. So make sure you're always having a number, a unit, and the chemical. And in your answer as well, you want the number, the unit, and the chemical, and the correct number of significant figures, which is awesome. So lots of things to think about. So now, though, to double check, our atoms of silver cancels our atoms of silver, and we are left with moles of silver on the top, which is what we are trying to find. So that's how we know that we are done making this train track, when the unit in the top right equals the unit that we were trying to find. So then we are going to multiply all of the numbers on the top and divide by all of the numbers on the bottom. So we get 2.80 times 10 to the 22nd times 1 divided by 6.022 times 10 to the 23rd. You'll notice that I have this in parentheses. And the reason that I have this in parentheses is because if you just punch it in straight like that, then because this has a times 23, it's actually going to think that that portion of it is on the top, and it's going to have all of your calculations wrong. So you're going to do, 2.80 times 10 to the 22nd times 1 divided by, in parentheses, 6.022 times 10 to the 23rd, and you will get your answer. So you need to also pay attention to significant figures. This has 3, this has 4, this is exact. So when we're looking at our significant figures, we're going to go with the one that has the least, right? So 3 versus 4, so our answer must have 3 significant figures. Okay. If you have bought the calculator that's the TI 30X2S, which is the one that I was talking about in that first day lecture, you can actually do this a little bit easier, and you can use this x to the minus 1 functionality. The double E button, which is above the x to the minus 1 functionality. So if you type it in, this mole, you can type in 6.022, and then you'll find the double E button. And like I said, I think it's above the x to the minus 1. So you're on your calculator, you're going to put second function, and then get that double E. So second function, x to the minus 1, or second function, right, double E. And it's going to put an E here, which stands for exponent. And then type in 23. So this 6.022 E23 takes the place of this times 10 to the, that E. Okay, so if we do 6.022 E23, then we don't need to use parentheses, which is awesome because I have found that there is a lot more sources of error when you're using these parentheses, especially if you have to keep continuing to use a bunch of parentheses. You could also do that with like the first number. You could put 2.80 E22. And this is going to work way better. So I know it's going to take maybe a minute to try this out on your calculator, but it's going to be really, really useful. If you have a Casio, you can also do this. There's a times 10 to the x button. It's down in the bottom right next to the equals. It looks like this, times 10x, right? And so you can hit that button and it's going to work essentially just like that double E. It's gonna write it out as 6.02 times 10 x 23. It's kind of how it's going to look. Okay, and that will work, like I said, like this double E button, and then also you don't have to use parentheses when you do this. So it's super helpful. I would try that out. Try it like this problem and see if you can get this answer without using parentheses, because like I said, it's going to save you a lot of headaches down the road, and it will actually save you a lot of time once you get used to it. Okay, so to count atoms by weighing them out, we need an additional conversion factor, which is the mass of 1 mole of the atoms. The mass of 1 mole of atoms is the element's molar mass, right? Because it's the mass of 1 mole, so we call it the molar mass. The element's molar mass in grams per mole is numerically equal to the element's atomic mass on the periodic table. So like if we think about carbon, the mass of 1 mole of carbon is going to be the mass on the periodic table, which is 12.011 grams of carbon. Okay, so this is going to be really, really helpful. The mass of that element on the periodic table is equal to 1 mole. So let's see how to use this. So this first one says, how many grams are there in 0.465 moles of silver? So again, we're going to put what we're starting with in the top left. Okay, so we're going to start with, there we go, 0.0465 moles of silver, and we need to cancel moles of silver down to the right and come up with grams. So when we're converting between moles and grams, we're going to use the molar mass. We know that 1 mole of silver, and we can go and we can look at the periodic table and find silver on there. The mass of 1 mole of silver, is 107.87 grams of silver. Okay, so again, when things are equal, they're going to get stacked, and so we need to figure out, okay, what goes in the, what's going to cancel out, what's going to go on the bottom. And so we have to cancel moles of silver with moles of silver down on the bottom. So 1 mole of silver will go on the bottom, which means that 107.87 grams of silver will go on the top. Double check moles of silver cancels moles of silver, and we're left with grams of silver up on the top, which is what we were trying to find. So then we can go through and actually do the math. 0.0465 times 107.87 divided by 1 gives us 5.02 grams of silver. And again, double check your sig figs, right? This has 3, this has 5, and this down here, this is exact. So 3 versus 5, our answer will have 3. The second one is going to use both conversion factors because we're going to go from atoms, we're trying to find atoms from grams. So we're going to start with our grams in that top left, 10.0 grams of oxygen, and we need to convert grams of oxygen into moles of oxygen. So we know 16.00 grams of oxygen is equal to 1 mole of oxygen. So we'll use that conversion factor to change into moles of oxygen. Right? So grams has to cancel grams, so our 16 grams will go on the bottom, 1 mole will go on the top, and we double check grams of oxygen cancels grams of oxygen, and now we're left with moles. But moles is not what we are trying to find. We are trying to find atoms of oxygen. So that's how we know that we're not done making this conversion, not done making this train track. So now we have to convert our moles of oxygen into atoms of oxygen, and we'll use Avogadro's number for that. So we know 1 mole of oxygen is equal to 6.022 times 10 to the 23rd atoms of oxygen. Okay, so again, we need to figure out, okay, what goes on the bottom? Well, moles of oxygen has to cancel moles of oxygen, so moles will go on the bottom, so this side will go on the bottom, and that 6.022 times 10 to the 23rd atoms of oxygen will go on the top. Again, double check, moles of oxygen cancels moles of oxygen. We are left with atoms of oxygen on the top, which is what we were trying to find. So we are done making our train track, and now we can go and plug it in. So we have 10.0 times 1 times 6.022 times 10 to the 23rd divided by 16 divided by 1. And I want to point out really quick that I have 2 division here, right? Divided by 16 divided by 1, because 16 is on the bottom and 1 is on the bottom. You need to hit division for both of those because they are both on the bottom. Sometimes people get into this habit where they go divided by 16 times 1 because 16 and 1 are on the same level. Okay, you can do that, but then you would need to put parentheses around the 16 times 1. It is cleaner if you just divide by 16, divide by 1, because they're both on the bottom. So just be careful. If you find yourself getting the wrong answer, it's likely because you did divided by this times this. Don't punch it in your calculator that way. Do divided by this, divided by this. Much cleaner. Then you need to go figure out your sig figs. We've got 3, this is 4, this is exact, and this has 4. So our answer can only have 3 significant figures, which is why we're getting that answer down at the bottom. All right, and that is the end of Chapter 2. We covered a lot of stuff in Chapter 2, but hopefully most of it is review from when you've previously had chemistry or you've had Chem 20. You can also now finish that Chapter 2 lecture worksheet. You should be able to do all of the problems on there. And you can also find more problems on that Chapter 2 study guide. And if you run out of problems there, you can also do the Chapter 2 problems out of the book that are recommended on that Chapter 2 study guide. One of the secrets to being really good at chemistry is to continue to do problems. I always say, keep working on problems, not until you get them right, but until there is no way you could get them wrong. There is no possible problem that anyone could throw at you that you could ever get wrong. That would be how you know that you've really mastered the topic. Also remember that on that Chapter 2 study guide, there's a list of topics and things that you need to know. Most of them will always be covered in lecture, but there are some of them that you're responsible for reading and learning about on your own. So make sure you go through that study guide, use it as like a checklist. Yes, I know this. Yes, I know that. No, I don't know this. Oh, I better go read it. It's a good idea to read the entire chapter anyway to really solidify your understanding, especially reading it before lecture is really helpful. But at the very least, make sure that you are reading the topics that are not covered in lecture to make sure that you're prepared for the quizzes and the test. So there you go. That is the end of Chapter 2. And as always, send me in any questions you have, and I'll see you all next time.